So welcome to lecture 36 of MCS 471. This is a lecture on numerical analysis, but it is an overview lecture in order to prepare for the second midterm exam that will happen on this coming Wednesday. There are two parts in this review. I will explain the way the second midterm will run. In short, it will run just as the first midterm, but if you skipped the first midterm, it's worth noting. And then I have prepared 9 representative questions. The questions with answers, so in a way it's rather unproductive to see the answers before you have had time to review. But also the slides are posted without answers, so you could eventually still look at the questions and then try to see if you can do them rather than look at the answers first and work backwards from there. So the questions are representative, but they're not exhaustive. So some of the questions you may be very similar. Some of the questions that you will get on the second midterm and there will always differences. Okay. So the second midterm happens this coming Wednesday at 10 o'clock, at the same time when we usually meet for class. The exam is an online event. That means that it's also an open book and an open computer. Well, you must use your computer. So that's the first important part. So it is an online exam. So it has to be done with the Jupyter notebook, and it has to be submitted with Gradescope. So that's the first important thing. The second important issue is that you must sign up for the exam. So there is a skipping policy. So that means that if you do not do anything, that's the default, then the 100 points for the second midterm are transferred to the final exam. So there may very well be good reasons for not doing the second midterm exam, but that's the policy. So the default is that if you do not do anything, you will skip the exam. You must decide by 5 p.m. on Monday, 15 November, by sending me an email that you will do the exam. If I will not receive that email, you will not receive any questions. So by this sign-up policy, I absolutely want to make sure that you at least spend some time questioning whether you are going to be prepared on the day of the second midterm exam. The exam comes in multiple versions, and it must be solved individually. So you are welcome to use all the materials from the course, and for some questions you must use the Julia functions that are posted, but the way the exam works is that it should also be your individual explanations that matter. So by explaining the results of the computations, I want to see that you understood the material. What is the material about? Well, essentially everything that has been covered since the first midterm. So we started with numerical differentiation since the fourth computer project was on numerical differentiation. I hope that all of you are familiar essentially with Richardson extrapolation. And it goes all the way through the last lecture on the Galerkin method. So the problems in this review are more or less equally divided. So I have 9 questions prepared, 3 on boundary value problems, then questions on numerical integration and differentiation, and then the initial value problems. This is not a programming course, but a computational course. So the concepts in numerical analysis are important. Homework is important. So that's probably what I have to emphasize here. The last review question is actually the solution to a homework problem, except with a changed coefficient. So please make sure that if you have made your homework and some things were wrong, that you understood how it actually should be done. So studying and preparing for this course is also by seeing all the problems that how they should be solved. So the Jupyter notebook is important. For issues of presentation, I still prefer slides. But one way to prepare also for the midterm exam, if you want to stick to the format of the review, would be to make a Jupyter notebook of the questions and answers that are covered here. All right. Once again, the most important action item, if you want to do the second midterm, is to send an email before 5 o'clock on Monday, 15 November. So the purpose of the skipping policy is that when you do the exam, that you will be prepared, and even already questioning, even already after the review, questioning and examining for yourself whether you are sufficiently prepared for the exam is already an important part of the preparation. A question that I often get, if you have taken the midterm with a disappointing score, then can you drop the midterm? The answer is no, but I do take into account that if your final is sufficiently better, then that bad midterm may not harm you that much. The same happens, by the way, with the computer projects. You can afford a bad computer project, but not so much a whole of bad computer projects. The same also for the midterms. So if you had a disappointing first midterm, then I hope that your second midterm will be better. We still have 3 weeks in the semester, and there are still a lot of important progress that can be made. Especially since one can actually see also the material that we have covered since the first midterm as an application of many of the concepts that we have seen. So here is the first question. The first question is on the construction of a quadrature rule with 2 points and 2 weights. We want to determine the points and the weights so that we have a highest possible degree of precision. So it's important that this is a setup question. So we will have a nonlinear system in the weights and the nodes. It's a setup. It's sufficient that you can formulate the conditions. And the second part is just as important as the first part. Justify. Why is the way you have formulated the setup, why is that going to attain a degree of precision as high as possible? Here it's now very good to question what is the degree of precision. In studying for the exam, it's very good to go back to the relevant course materials, the relevant lecture that we have seen. During the exam, if you have to verify what is the highest possible degree of precision, then you are going to get into time issues. So if for every question you must consult the lecture, it will not go very well. I should also say that the method of undetermined coefficients also appears with the construction of methods to solve initial value problems. So we have seen the Adams, Bashford, Adams, Moulton's methods. The construction also follows the same pattern as the method of determined coefficients. This is a hybrid question also here. We have seen Gaussian quadrature. So if we would solve the system that we're going to set up, then we will have a very particular form of Gauss-Legendre, which is by default on the interval -1, 1, but here it is tailored for 0h. All right, so let me look at the solution now. So the high degree of precision means that polynomials up to the highest possible degree are integrated correctly by the rule. Here the rule has 2 points and 2 weights. So we have 4 unknowns. So we expect to go as high as the cubics. So formulating this for the standard basis, so which is not a good idea to do, but for small degrees it works. So we have seen Gaussian quadrature, and we are actually now constructing a Gaussian quadrature. So this is the system. I have left the integrals of the basis functions unevaluated. So this is not a course, this is not a calculus course, and one can quite easily set up the SymPy instructions to integrate these integrals. But here we have the system that need to be solved in order to have a degree of precision up to 3. So this is the justification that comes of this. It is important, if this question would be on 15 points, then you would get 10 points for the equations, but you need to write at least 1 sentence. So here is the sentence. We have seen extrapolation, both for computing derivatives and for doing integration. So I will spend equal amount of time on this in this review. Note that there are several versions of the exam. One version of the exam will be Richardson extrapolation. The other exam will be on Romberg integration. So don't skip. I'm hoping that because of project 4, that one is better understood than the other. So here is the question. We have a very nice test function where we know the derivative already. So the derivative of the exponential is again the exponential. So we are computing e to the power 2, where e is the transcendental constant. We compute forward differences. Forward differences have a low degree of accuracy. So we are computing them also for very, very large values of h for 1 already. So compute the forward differences, then apply extrapolation, and to improve the accuracy, which will in general not be that high, and then justify how many decimal places are correct in your answer. Here the justification can take two forms. I'd be working with a very basic function, and in general, if it's more complicated, you can always use SymPy to compute the derivative and then compare with the numerical approximations with the exact value. That is fine. But in general, if you would not know, you could also rely on the Taylor series expansion. The Taylor series expansion that gave us the forward differences. So in studying again for this question, would be very good to look at lecture 24 and write down a Taylor series expansion. And what extrapolation does, extrapolation is making linear combinations. It's then actually solving a linear system. It's making linear combinations to eliminate the error terms from the Taylor expansion. Here you must use a Julia function. So we have the Julia function that is in the program Richardson, and in this, so you can look at the program, or you can also look at the Jupyter notebook. It's important, again, if you have never done this, and with project 4 this is now very unlikely, but on the exam, if you have never done this, then reading the specification and knowing what to adjust may be time consuming. So please look at one of the homework exercises, or do the answers in a Jupyter notebook in preparing for the exam. So in preparing for the exam, if you only have 50 minutes, make a Jupyter notebook from the slides. Here is the numerical output, two tables. So the first table starts with the forward differences. So the first column here gives the forward difference. So you see that all the numbers are changing. So, and you essentially only have one decimal place correct. But the accuracy actually improves. So at the end, we do, if we just compare the same number of decimal places, then you see that we have about 3 decimal places correct. So by the way, I gave now a third good justification. So you look at the last row at the table and you underline the matching decimal places. This is a very commonly used technique to estimate the errors. So it will be an upper bound on the error. So here, if you really are strict with comparing the digits without considering the rounding that may happen, then you could say that we have at least 2 decimal places correct. But you see the 3 decimal places from here. You could also do the justification differently. So here we have OH, h squared, h to the power 3. So, and h is about 1/8 here. It's not even 1/10. So that's why we don't really have h to the power 4 at the end with 4 steps, because our step size was so high. And also in the big O, there is a constant that should not be ignored. All right, Romberg integration is the same idea, although here we rely on the Euler-Maclaurin summation formula. And remember the Euler-Maclaurin summation formula assumes that the integrand is sufficiently many times continuously differentiable. So that is an important condition that needs to be satisfied here. So one alternative question on Romberg integration could be, does Romberg integration apply? Here for the exponential, which again has very nice derivatives, it's always continuous derivative, differentiable. So Romberg integration on the exponentials is quite nice. Again, with calculus, we know the exact value. So justifying how many decimal places in the answer are correct can be done in a very straightforward manner. So notice here that we have two different questions, Richardson extrapolation or Romberg integration. For the Romberg integration, there is a variation here in a third version of the exam that will ask you why can you apply Romberg integration. Refer to the continuously differentiable nature of the integral. So we have seen improper integrals that this may be a danger. All right, what's the solution? Again, here you need to apply the program Romberg. So there's a function in Romberg. Either you do this at the command line, but since everything needs to be submitted in a Jupyter notebook, please do the program from within a Jupyter notebook. And if you get a question on Romberg integration, you will be able to solve it much more quickly if you have already practiced it. So here is the output of the program. The composite trapezoidal rule runs very slow, and that's the main motivation for Romberg integration. So with the same number of function evaluations, or equivalently put, without any new function evaluations, we get a 10 decimal places accurate result. And here the progression of the last line is very obvious. This is a very nice progression of the course. So each time when you do one extrapolation from one column to the next, you actually gain 2 decimal places. So that's the first part on integration and differentiation. Then we come to the ordinary differential equations, and I have prepared a number of representative questions. So we have started out with the first order standard equation, the test equation, but any higher order equation can be rewritten as a system of first order equation. So here we have an initial value problem of third order. So the triple, so the equation can also be formulated with the 3 and then between round brackets here to indicate that this is not a power. We have the third derivative. So we have a third derivative. That means we need 3 initial values in order for this problem to have unique solution. So this problem is a homogeneous equation. Homogeneous being that there is a 0 right-hand side. So the question has 2 parts. Rewrite this third order differential equation as a system of first order differential equations. And since this is a homogeneous problem, then knowing the roots of the characteristic equation of this problem will determine the asymptotic behavior of the solution. So typically, initial value problems, we also always solve them on a restricted domain, but for certain types of problems, and this was a problem that is a linear problem, so we can actually solve it in great generality. So it's a linear system. The linear system will become apparent by rewriting it. So we start from a third order equation, and we are going to have three equations by introducing new variables. So the first variable is the original variable y, the second variable is its derivative, and the third variable is the second derivative. But intermediately, you can actually then see, so here my answers are elaborate because they also are the explanations. So the straight answer is actually this system here, where you always have the same pattern, where your right-hand side consists of the new variables. So y2 is new, and it is the derivative of y prime, and y is y1. So that's why we have this equation now reordered. And also the coefficients, the original coefficients that are in the third order differential equations appear in the right-hand side. So we have a right-hand side where the coefficients are here. Now, linear systems, we always write in a matrix form. So we can rewrite the equations in the matrix form. And this introduces, so any form here, so the answer to the first question is either the matrix form or the three equations that you give. So in the explanation, the matrix form is better as it introduces the answer to the second part. What does this buy us now? Well, the matrix has a very particular form which we encountered several times in this course. It is the companion matrix of the polynomial. Companion matrix is the matrix associated with the polynomial. So you can also see this as a root finding problem, reducing it to the eigenvalues. Or here, the way the question is phrased is that through the characteristic equation, we can determine the general shape of this homogeneous equation. So we have a third order, so we have three basis functions. In the examples that we used for the 2-point boundary value problems, our linear problems always had two basis functions. So the degree of the equation determines the number of basis functions that you have. And for a linear system, they are exponentials. But the exponentials can have multiplier that is complex. So here, this is where the periodicity comes in. So we do have an oscillating behavior. But the question was not so much about this oscillating behavior, but whether the long-term behavior is converging, decaying, or if it is growing exponentially, diverging as time goes on. And here we look to all the magnitudes of the eigenvalues, and all of them are less than 1. So this is still a paper and pencil question, but of course, in a Jupyter notebook, you can very easily check the absolute value of these complex numbers. So the final answer is that the solution decays. The justification is that is this formula here, so that you write up that we have three basis functions and the lambda 1, the lambda 2, the lambda 3, the three eigenvalues, which are the roots of the characteristic polynomial of the companion matrix, are actually determining the long-term behavior of the solution. A variation on this question is the stability of a method. So in a multi-step method, so we have two steps. So we distinguish in our methods for solving an initial value problem a one-step method, where we compute an approximation for the next point by adding something to the current point. Here we have also the current point, and then also the previous point comes in. So this is the previous point that I'm just underlined. So this is a two-step method. For the stability, we actually don't really look at this part here. So is this method stable or strong or not? So this is a question that looks entirely different from the previous question, but it is extremely related. So it is an alternative, another version from the previous question. So is this method stable or not? You will set up a characteristic polynomial. A method that is not stable has the risk to drop on spurious trajectories. So we have initial values with initial conditions that sometimes are not so precisely known. So an unstable method is a method that should be avoided. So there are two parts. So the first part is to set up the characteristic polynomial. And look then at the roots. If the roots would be larger than 1, then the method would not be stable. Here, the method is stable, and it is also strongly stable. Again, if on the exam you will need to consult the definitions, then the exam you may risk again to run out of time. Now you know the definitions because of the review, but be aware, let them sink in. So again, even if during the exam you will need to look at the slides, it will be a longer exam for you. So a very good way to prepare for the exam, to focus on the essentials, would be to get a Jupyter notebook ready. So in then stating the answers, you will need to change the numbers to the problem. Predictor-corrector methods. So here we have the standard formulation for an initial value problem. And the predictor-corrector method that we are using uses 4 points in every step. Now, what matters with differentiation, integration, and but what mattered also with root finding was how many times do you evaluate that right-hand side function. So this particular question is on the cost. Now, backtracking on the previous problems, we have seen Richardson extrapolation. How many function evaluations should you do? We've seen the trapezoidal rule with Romberg integration. How many function evaluations are you doing? We have seen the initial value problems now. How many function evaluations do you do? So we are interested in numerical analysis in computing accurately and efficiently. So this is an efficiency question. So we start at 0 So that is our standard time step, or also space step, and we want to go to 1.4 and starting with a step size 0.2. So this will cost 7 steps, but we are using predictor-corrector methods that are using 4 function evaluations in every step. So how many function evaluations do we do altogether? So the back of the envelope computation might suggest 4 times 7, but that is wrong. So let me justify what is the correct count. So 4 points means that in a predictor-corrector means that we are using an Adams-Moulton as the corrector and an Adams-Bashford as the predictor. Both of them have the same accuracy. The local error is the number of function evaluations. The global error is the number of function evaluations that we do. And the predictor uses the previous function evaluations. The corrector does 1 new function evaluations. So what is important in answering this question is to draw first the discretization. So going from 0 to 1.4, where we do 7 steps, and then we mark the predictor-corrector methods. So now you see that the answer would be even 8 function evaluations, and not times 7 times 4, but also that example is that answer would be wrong because you cannot use the predictor. So here the predictor uses, so suppose that, so the last time we could use the predictor was when we were here, because then we had the 4 previous function evaluations. So we are not doing any new function evaluation except here at x4 to get to the step. So we cannot use the predictor-corrector methods to get to this point. So this is a question about predictor-corrector methods, but to answer them, you actually need to know that Runge-Kutta methods are one-step methods. But they have the same accuracy. So we are using a 4-stage Runge-Kutta method that has a global error of h to the power 4 and local error of h to the power 5, uses 4 function evaluations. And this completes the exercise. So Runge-Kutta is used first to compute y1 with 4 function evaluations, then y2 with 4 function evaluations, then y3 also with 4 function evaluations. And then you can go to the next step. So this gives then a total of 20 function evaluations. So the number 20 is important, but just equally important, I've given already 2 wrong answers. So even if the 20 would be correct, without justification, if this question would be on 15 points, you would only get 5 points. So you should at least draw the line and indicate where the numbers come from. So you should mention, your answer must mention Runge-Kutta method, even though this is a predictor-corrector method, predictor-corrector question. All right, we're moving along in the last chapter now. So in the remaining 10 minutes, I will try to sketch the answer to 3 questions on boundary value problems. So shooting methods. Here is shooting methods reduce the problem to an initial value problem. So this is one type of boundary value problems. We can formulate 3 other ones. So there will be 3 different versions of the exam. So note that you must consider the shooting methods where the values of the derivatives are given. So what is the difference if you think about it in more geometrical terms? With shooting, as the problem is formulated here, you lack the initial slope. So you are adjusting the slope in order to reach a target. When you are given the derivatives, you have a fixed slope, you have a fixed gun, but then you're sitting in a tank and you're moving forward and backwards. So then you guess what is the right position in order to reach either then the incoming slope, if it would be a Neumann problem, or the target, if it would be a mixed problem. What is important here in this question is, and especially for this part here, and is that you make the distinction between a linear problem and a nonlinear problem. So this is a linear problem, even if the solution is a quadratic. So it's a linear because the right-hand side is extremely simple. So you must recognize when a boundary value problem is linear or nonlinear. When it is nonlinear, then we are very close to the root finding problem, where either we then apply the secant method or the quadratic extrapolation. So the technical aspect of this question is applying interpolation a la Lagrange. So we have an interpolating polynomial where the input is the guess. So we have done two shots here for y1 equals 0, y2 equals -1, with corresponding endpoints 7 and 5. So we construct the interpolating polynomial. So you can see the correctness, y equals 0, we have 7. And we solve this polynomial so that the next guess equals 0. And in some sense, this is a little bit unfortunate. Why do we have this 0? Well, we have this 0 because, and I must underline this here, because here we have the 0. All right, so it's not always so that we look for a root of the interpolating polynomial. So the boundary value problem is linear. So the coefficients are independent of x and y. That means that we don't need to run essentially the extrapolation again, and if we retained all the points in our initial value solver, we can actually construct the correct trajectory by simply interpolation. So that could be a variation. So given now the trajectories, compute the coefficients that will tell you for any intermediate point. So we went from -1 to 1. At 0, suppose we have the value of the first trajectory and the second trajectory. How do we compute now the intermediate value without running an initial value problem solver again? All right, the second method that we covered for solving boundary value problems was the application of finite differences. So we are constructing a linear system. Setting up the linear system is the first part. In the second part, what is the expected accuracy? So one can solve both questions by looking at the discretization equation. So we will replace the second derivative here by this formula. So the 1, -2, 1 will always show up in your tridiagonal system. What may be different, so this is a linear problem again. What may be different is that there are other terms. So if the equation, the right-hand side, would have involved a y, or more non-linear y, think about the pendulum problem where we have sine of y, then that would be also reflected in your equations. So you would have a non-linear system. Again, it's important here to recognize if your system is linear or not. Here the right-hand sides are changing. And the final answer is actually this. Notice here, so in my answers, I'm a little bit more elaborate because I'm realizing for some of you this might be still very unfamiliar and the first time you look at this. So, but notice that always the circled, what I've now circled, are actually the boundary conditions. So here you only see a -1, but you don't see a -0. That's because y4 is 0. But again, as a check for a linear boundary value problem, this is the shape of your linear system. So this is for 3, because both fits nice on my slide. In your Jupyter notebook with your Julia functions, the setup from the posted Jupyter notebook, you can actually go as high as you like. And this then becomes the second important part. What is the expected accuracy of your solution? And here we have the square. So even already with this very coarse grid, we could expect 2 decimal places correct. All right, I have 4 more minutes for the last question. So the last question is the same boundary value problem. Again, it's important to recognize that this is linear, and we will again have a tridiagonal linear system. So it is the same result that we will getting, and the same questions that we are asking. Set up the linear system, and what is the expected accuracy? The equations depend on a basis of spline functions, of linear spline functions. So the solution that we are getting is piecewise linear. And because of the property of the piecewise linear, because of the spline functions, the 10 shape of the functions, we do have 3 terms equation. And they always look the same, at least for linear problems. So notice it's very important to make the distinction whether there is an x at the right-hand side or whether there is a y. Because there's only an x here, the x will only show up in the right-hand side, not in the left-hand side. So if you look at the lecture slides now, a variation would be of this question would be 8 times y. So it's important to notice that. So then we have an entirely different linear system. You may use the formulas for the integrals, for the inner products from the lecture. The setup function from this lecture also defines them. You can also use SymPy, or there is actually also a numerical integrator in SciPy. But the importance of the question is how to set up the system. And here is the result in 2 ways. Either you leave the h in the inner products, or you can simplify. The simplified version has again the virtue that you do have the 2's on the diagonal and the 1's on the lower diagonal and the upper diagonal. Because we had the x, only the x at the right-hand side, it will also show up at the right-hand side. So in the lecture example, it was a y at the right-hand side. Know the difference between the 2 here. And again, the answer is essentially the same. The accuracy, the expected accuracy, is the same for this method as well. So we also expect, even with the large step size of 1/4, to have two correct decimal places. Most important slide is the last slide. So I could, in 50 minutes, only talk about 9 questions, but there are a lot of modifications of the questions that are presented here, and there will be at least one question that is not taken verbatim from the review.